Okay, next I want to point out another useful fact, and which says that the power rule also applies to non-integer powers. And that's what this next handful of examples is here to illustrate. So if we look at the first example, by the way, we're asked to find the derivatives of the following functions, right? So that's what we'll do for all four of these functions. So the first one, f of x is equal to x to the 1/2, you can see that's a fractional exponent. So for that one, well, based on the fact, it says the power rule applies to non-integer powers, right? And of course, if you go back to the way it was stated, it said the power rule says that if you let f be defined in this manner, be any function defined like f of x is equal to x to the n, where n is any constant real number. Like real numbers are vast, right? That certainly includes fractions and even irrational numbers. So that's what we'll take advantage of here. So if we've got f of x is equal to x to the 1/2, we can go f prime of x, and we'll just apply the power rule. So we'll put the exponent down in front, 1/2 x, and then the new exponent will be 1/2 minus 1. And you can just do some rough work off to the side. This happens sometimes when you've got fraction arithmetic. Sometimes it's nice to just work out the details off to the side. So if I go 1/2 minus 1, remember I can go 1/2 minus 2/2, which is negative 1/2. Right? So I'll take advantage of that here. We've got 1/2 x to the negative 1/2. And, well, there's nothing wrong with leaving it like that, but if I personally don't like negative exponents, so I would take it one step further and I would rewrite this so the power of x is on the denominator. So I can write this as 1 over 2x to the positive 1/2. So that's just a way to rewrite this now. They're both equivalent, of course, right? But this one has no negative exponents. So that's where I would stop with that one. Okay, and I'm just going to put a box around this. I'm not going to say therefore f prime of x is equal to 1 over 2x to the 1/2 this time. But that's okay. It's good enough to just identify this because look, I can trace it back through the chain of equal signs to get to f prime of x. So it's automatically implied that this is equal to f prime of x, and it still has the effect of drawing a reader's attention to the answer. So that's why I'm doing that. Okay, and for part B, let's look at another example. So we've got g of x is equal to the cube root of x plus 10x. Now, the cube root of x, that's not a power of x, or at least it's not written like a power of x, but we actually can write it like a power of x. So before we do any differentiation, we're just going to rewrite the function so it actually looks like something that we can handle. So let's just rewrite the function g of x. Well, it's the cube root of x plus 10 of x, or 10, I keep saying 10 of x, I meant 10x. So it's g of x is the cube root of x plus 10x, and I'm just going to rewrite this so it's x to the 1/3. Because that's another way to write the cube root of x. So I have x to the 1/3 plus 10x. And why do I care? Why do I want to bother with this other way of writing it? Well, that's a power of x now. It's a little bit more easy to see how you would use the power rule here. Okay, so let's actually take advantage of that. So now I can say g prime of x, and then we'll just do the power rule on these two terms, right? So if I do the power rule on x to the 1/3, I'm going to get 1/3 x to the negative 2/3, right? And if you don't see where that came from, really I just went 1/3 x to the 1/3 minus 1. I'm just going 1/3 minus 1 is really 1/3 minus 3/3, which is negative 2/3. So that's where this exponent came from. I'm just applying the power rule carefully to this term, x to the 1/3. Okay, and then the 10x term that comes after, well, you can just take advantage of this note we made on the previous page, right? If you have a constant times x, its derivative is just going to be that constant. So in this case, our constant is 10, so we're going to have plus 10 for the derivative of that term. Okay, and technically this is correct, but I'm going to argue that this is not a good way to leave it, because in our example, like here we had a fractional exponent. It's negative and fractional. Well, let's get rid of the negative exponent first, and then I'll look at why we should still go further than that. So first I'm going to write this as 1 over 3 x to the 2/3 plus 10. And then you might say, okay, why don't we stop here? Because on the previous example, we stopped in this form, right? 1 over 2x to the 1/2. And I'm going to try to point out the difference between example A and example B. In example A, we already had a fractional exponent in the way the function was written down. But in part B, the function was written in radical form. We introduced this fractional exponent by actually just writing the function in a different form. So out of courtesy to whoever gave you this function, if you can imagine this as a situation where someone gave you a function and asked you to find the derivative, and you're going to now give the derivative back to them, you want to give it back in the same form as the function that they gave you. That would be the best possible answer. So let's actually convert this expression down here into radical form, just because the function that we were given in part B was in radical form as well. So this is really 1 over 3 times the cube root of x squared, and then plus 10, like that. And that's the best answer. Is it wrong to leave it as it was? Is it wrong to leave it like this? No, it's not wrong. It's just much better to answer it like this, so you'll see me do it that way, just to try to make that point. Okay, let's look at part C. We've got h of x is equal to x to the 1.1 plus 10 times x, and then here we've got to actually have an irrational exponent, right? Our exponent is the square root of 2, and that's no problem. We can still apply the power rule when our exponents are irrational as well, so there's nothing stopping us. It looks a little bit weird, but we can still handle this the same way we handled the other problems. So our h prime of x for part C, well, the first term, we have x to the power of 1.1. If you do the power rule on that term, you're going to get 1.1 times x to the 1.1 minus 1. Right? That's the first term. And then now for the next term, we have 10 times x to the square root of 2. Let's do the same thing we did before. We'll just write down the multiplier of 10, because that 10 is just going to get pulled off to the side and multiplied on after. Really, the power rule is being applied to the x to the square root of 2. So inside these brackets, we'll put the derivative of x to the power of the square root of 2, which, if you use the power rule, you're going to get root 2 x to the root 2 minus 1. It looks a little bit weird because the square and the square root of 2 is an awfully weird exponent, and that's why this looks weird. But there's nothing stopping you from using the power rule, even if you have weird exponents, as long as they're constant. Right? That's a key thing. It's because this exponent is constant. That's why we're allowed to do this. Okay, let's clean this up a little bit. We can go. This is 1.1 times x to the 0.1 plus 10 root 2 x, and then for the exponent on x, root 2 minus 1, you're not going to do any better than that, right? You can't make that any more clear. So we're just going to have to, unfortunately, leave this as the square root of 2 minus 1. That's as simple as it gets, if assuming you do want to still be exact, which we do. Okay, and then now you can argue whatever, you can chase whatever form of answer you want, but at this stage I would say this is totally fine. Yeah, we've got decimals in the exponent, but so did the function we were given, right? X to the power 1.1. So I could write this as 1.1x to the 1/10. I could turn the 0.1 into a fraction, right, and I'd have x to the power of 1/10, and then I could write that as the 10th root of x. If I really wanted to, I could go ahead and do that, but it's not necessary. And I would say we're leaving this in the form that the original function was given, so that's probably the best bet. Okay, and we've got one more example in this list. So, and I'll just write down the function because it's going to be convenient to have it in front of us. In this case in particular, we've got x cubed plus 1 squared, and that's the function we want to take the derivative of. Now, that's not just a power anymore, right? It's x cubed plus 1, all inside brackets, and all of that is raised to the power of 2. So it's not obvious that the power rule is going to apply here, right? There's certainly exponents, but they're not just powers of x, right? There's a power of x cubed plus 1. So in this case, if we want to use the power rule, we're going to have to change the way this is expressed. So the best way to do that is to probably write this as x cubed plus 1 times x cubed plus 1, and then FOIL everything out. So what are you going to get? You're going to get x to the power of 6 plus x cubed plus 1. And if you combine your like terms, you're going to get x to the 6 plus 2x cubed plus 1. And then now, by doing that little bit of work now in advance and expanding everything out, you can see, well, this is a polynomial now. So this we can actually do this term by term using the power rule on each term separately. So that's what we're going to do. So I'm going to write this in Leibniz notation, dy dx, the derivative of y with respect to x, and I'll just differentiate each of these three terms separately. So the first term, x to the 6, use the power rule, and you'll get 6 times x to the 5. Now the second term, we've got 2x cubed. So again, I'll put the 2 off to the side. We'll write the 2 down so we don't forget, and then we can multiply it back on after, but focus on the power of x, which is x cubed. So using the power rule on x cubed, you're going to get 3x squared. And then finally the constant term 1 at the end. Derivative of a constant is just 0, right? So you're going to get plus 0. Okay, now it's just a matter of cleaning things up. We don't need now that we've finished, we don't need the plus 0, and this can be combined into 6x squared. So we get 6x to the 5 plus 6x squared, and that's a perfect place to stop. It's all expanded nicely. So that's our derivative of y in this case, and I forgot to put a box around the previous example, so we can do that now. And so that's really everything I can fire at you in terms of things you can do with the power rule. So I hope that's a good enough variety of examples. The rest is just comes down to practice, and you get more and more proficient the more you do it. One piece of advice I have for when you go to do the exercises: don't try to rush. Just focus on doing them properly. Write the steps out carefully, and you will get faster as time goes on. But if you try to worry about speed and focus on getting them done fast right off the bat, you just don't get as much out of your time investment. So please take me seriously on that. Write things out carefully. I promise it will get faster as you gain confidence. Don't worry about the speed. The speed will come.